Thanks, Sean, for the introduction. Thanks everyone else for being here. For a lot of you, a lot of this is going to look familiar, which I think is okay. And hopefully there's something a little bit new for at least most of you, if not for everybody. Like Sean said, I'm going to be talking about whether theory of mind is analogical. And to spoiler the rest of the talk, I think it is. And we'll go through a couple of experiments to kind of see what the evidence for that might be. So to begin with, what is theory of mind? I take a very broad view of what theory of mind entails. I view it as general reasoning about the mental states of others, right? So things like beliefs, desires, intentions, goals, anything that can be helpful for our social interactions, but that we can't readily observe from the outside. And so I can't see what somebody else knows, but I might be able to infer it based on what I know about them, what I've already watched them do, that sort of thing. And that inference can then help me hold an interesting conversation or otherwise think through an interaction that I'm having with that person. So it's a very, very much a huge part of our day-to-day. And because of that, it's probably not too surprising that theory of mind has been really widely studied since at least the 80s, under a few different names, but as theory of mind also. But even though it's been studied for such a long time, there's a lack of consensus on many of the key aspects of theory of mind, right? Everything from what processes are used in reasoning to how children develop theory of mind and even whether they develop theory of mind. Almost everything about it, there's some sort of debate that has maybe fizzled out, but never really settled. And the reason for those ongoing debates is that for just about every prevailing theory that there has been a lot of kind of contradictory empirical evidence. So somebody proposes a theory, as we're all used to, somebody else tries to disprove it, and this just keeps going on and on. So what I'm going to try to argue today, and I'm going to be very direct about this because we're kind of among friends, is that I think that the reason why there isn't really a consensus yet is because analogy hasn't been the prevailing theory of mind yet. So the prevailing, what I think analogical theory of mind should be, is through this analogical theory of mind cognitive model. And the cognitive model has three main claims that we're going to go through. First of all, and the broadest claim is that theory of mind reasoning and development occur through analogical processes. A little bit more specifically, reasoning occurs in working memory with occasional retrievals from long-term memory kind of on an as-needed basis. They might be triggered by things like surprise or the need for more information. And that reasoning itself is mostly driven through candidate inferences through analogical alignment. AToM is fully implemented in the analogy stack of the companion cognitive architecture. So all of the models I'm going to discuss here are implemented that way. I'm not really going to talk much about the specifics of the implementation, but it really is just sort of the one implementation using that analogy stack. By analogy, I mean structure mapping. So let's go through what structure mapping looks like when we're thinking about theory of mind. I'm going to use examples here from an experiment by Hoyle et al. From 2015. Have that citation a little bit later. So suppose we are thinking about these two little girls here, and let me pull up a laser pointer. And on the left, we have Alice. And Alice knows that she's looking at a box of cereal. And we know that she thinks that there is cereal in that box, right? And we get that from the picture. Suppose we then get this picture here of Kim, who knows that she's looking at a box of Legos. And we might ask ourselves, well, what does Kim think is inside the box? So through structure mapping, we can make a prediction about what she might think. And the way that we would do that is by finding correspondences first between the predicates. So nose matches to nose, container of matches to container of, and then based on those correspondences between their arguments or between the entities in those cases. And so the Alice and Kim are going to match to each other, the boxes are going to match to each other, and then cereal and Legos are going to match to each other. So even though they're different things, because they're the same, their argument to the same predicate in the same spot, they're going to match to each other anyway. And based on that alignment, we can make a prediction or a candidate inference. In this case, we might predict that Kim thinks that the box has Legos inside. So using that alignment, we can make this prediction that can answer a question for us. And this kind of inference is what most of theory of mind in the AToM model is. The other part of what theory of mind is, especially on the development side, is analogical generalization. And analogical generalization starts from the same alignment, but when we're given those two cases here about Alice and Kim, the alignment kind of collapses into a single case. And from that, we might say that, or we might learn that when someone, specifically in this case, when a little girl is looking at a box with something colorful in it, she might assume that that same something colorful is inside that box. And through that process, these stories or these memories or these things that we're learning can become schematized, and then as they become schematized, they can start acting as rules. And those rules can also play a role in theory of mind reasoning, in part because they can be retrieved and used in the same way as these initial stories were in the past. So to walk through this step by step, right? AToM is going to use analogical alignment for reasoning, analogical generalization for learning, mostly. And let's step through exactly what that means, starting kind of from a blank slate. This is based on an experiment, like I mentioned earlier by Hale 2015, and it's modeled in our 2017 paper. So we're going to step through this as if we're starting from a blank slate, like a child might in an experimental setting, right, where they've never been, they haven't heard the sort of thing that happens in that setting before. So we have Alice, and we hear that Alice is looking at a box of cereal. She thinks there's cereal inside, and hey, it turns out that there is in fact cereal there. And it's a fun story, and it is going to go into working memory. Right? So I want to pause for a second to back up. I tend to go back and forth as I talk about what's happening in the child's mind, what's happening in the model. That's because for me, they're kind of the same thing, right? I'm trying to model exactly what it is that's happening in the child's brain, in the child's mind, but they're interchangeable, and I'll try to stick to one or the other. Again, this is all fully implemented. This is what's happening in the model. This is what we think is also happening in children. So once we have that story in working memory, we might get another story, right? The story about Kim that we talked about, that we saw earlier. And that story is going to be structurally very similar to the story about Alice that we just heard. And because that's going to be relatively easy to retrieve the story about Alice from our working memory, and we're going to kind of make some inferences based on that if needed, right? So maybe we don't know yet what she thinks is in that box, or maybe we don't know what's actually in there, but based on that retrieval and the analogical alignment that comes out of it, we can make that prediction. Because they really are all that similar, that alignment will also lead to a generalization, right? So now we know that when people, little girls, look at boxes of colorful things, they might think that those colorful things are inside those boxes. Then when a new story comes in, right, this time she's looking at a box of crayons. She expects there to be crayons inside, but there are actually rocks in there. That same story is going to be retrieved, right? The generalization that we just learned, even though that generalization is actually incorrect in this case. But structurally, they're very, very similar. And so we'll get that retrieval, but we'll spot that there's something wrong, that there is a difference. Whether this is going to be through experimental feedback, like in the Hoyos et al. Study, or just through living life and being told that, you know what, that assumption that you made, that thought that you had was incorrect. So based on that, we're going to be surprised. We're going to be surprised that something so similar turns out to be incorrect. And we're going to try to search for an answer. And in this case, searching for an answer is going to look like retrieval from long-term memory. I'm sorry, something's a little wonky with my animations here, but it's going to look like retrieval from long-term memory of some story that would explain the situation. So maybe I'll remember how one time I went to a magic show, there was a magician who showed me that there was nothing inside his hat, but then he pulled out a rabbit. And I was super surprised, and it was weird that there was something different from what I expected inside his hat. And from that, we will form a generalization as well. So now our working memory has two generalizations. And next time we see something interesting, we now have two different generalizations to reason off of. That the new generalization that we formed, this one, the one with the retrieval from long-term memory, might then get later stored to long-term memory. We don't make specific claims about when learning kind of moves from working memory to long-term memory, but we assume that it does. And I do hope that in the future, we'll be able to kind of explore that transition between working memory and long-term memory a little bit more concretely. But for now, we'll assume that it does, and that's how a lot of learning happens in the analogical theory of mind model. I'm very tempted to ask whether there are questions at this point, just because we're halfway through the semester and that's what I do. But I know that that's not really how this works. So we'll move on. Unless there were questions, Sean, that you wanted to voice for people. No? Okay. You're kind of on the side screen, but I did see you shaking your head. Okay, so in that case, let's move into the theory of mind debates that have plagued us for decades, being a little facetious, right? But they really are major debates that haven't been settled, despite the fact there have been conversations about them since literally the 1980s, right? 40 plus years. The biggest of those debates has historically been whether theory of mind is theoretical, in the sense that whether the way that I think about other people is through a theory that I have about them. And so I have a theory about how people's minds work and what makes people make certain conclusions, what makes people think certain things, know certain things, maybe as a set of rules. Or is theory of mind a simulation, where in order to think about what someone else might know or believe or what desires they might have, what I need to do is simulate the situation that they're in as if I were the one doing it, and then make a prediction based on what I would believe or know in that situation. The other big debate is whether theory of mind is developmental or whether it's innate. We know that young children perform very poorly on theory of mind tasks, and we know that they tend to master them by about age 5. Some researchers argue that this is actually just because of verbal skills. So before about age 5, they don't have the verbal skills to tell us what they're thinking, right? To express their theory of mind knowledge, or they might not even just not understand the task that we're asking them to do at that point. Others argue that there's more to theory of mind development than just the fact that you're getting language skills and are therefore able to express something that's innate. But language itself does play a causal role in theory of mind development. So there's of course, more to this developmental versus innate debate, but the role of language tends to play a very big part. The other question that tends to come up in this conversation is the kinds of mistakes that we make in theory of mind into adulthood, right? And whether developmental accounts versus innate accounts would explain why those mistakes happen, because it turns out that they do. We'll start by talking about the theory versus simulation debate, because that one, honestly, with AToM is kind of a quick summary to get through. AToM is the thing is that AToM is kind of both. And so it's a hybrid model that can do reasoning that's theory-like and also simulation-like, and importantly does it through the same processes. So as simulation, we're thinking about AToM as when it's retrieving memories of the self. It's when you retrieve a memory of yourself, it's what did I think, or what did I know, or what did I believe in a similar situation? And that's very similar to actually going through the steps of simulating of what you would do. It's just kind of a past tense version of that. And so with the example of the rabbit in the hat, right, it's as if I was simulating that being the little girl with the crayons in the box and finding something that I didn't expect in a container where I expected it to be. On the theory side, this goes back more to what we were saying about generalizations becoming rule-like. And because AToM retrieves those generalizations and uses them in exactly the same way as it would individual memories, it ends up acting almost like a theory, or rules that can be used as part of a theory. And again, importantly, it's all part of the same process. So AToM doesn't necessarily answer the debate between theory and simulation, but it kind of says, why not both? Right? We can do both by the same process. And because of that, we kind of cancel out some of the evidence against each of them, kind of best of both worlds sort of approach. So for example, when we're talking about theory, one of the biggest pieces of evidence that people will say that theory doesn't account for is an egocentric bias that is seen in a lot of theory of mind reasoning. What I mean by that is when people perform theory of mind reasoning, often they will make assumptions that are much more similar to themselves than you might expect based on what they know about the other person. And AToM explains that with those egocentric memories, right? If my memory is about myself, then my projection or my inference or my prediction will also be based on what I know, what I do, kind of who I am. On the other hand, on the simulation side, the biggest argument against simulation is the developmental trajectory of theory of mind. So I mentioned earlier that there's this other debate between whether theory of mind is developmental or innate, but in either case, there is a trajectory of children start not knowing theory of mind, and then they do know theory of mind. And simulation doesn't really give a good account for why that would be, regardless of whether you take the language, just getting the verbal skills is enough point of view or not. There's just not really an account for development within simulation. AToM says, you know what? Actually, we can account for development. And in this case, it's going to be through updates to generalizations or just kind of ongoing learning. So given that, I'm going to change into talking about developmental versus innate debate, just because I think that one's maybe a little bit more interesting, and we'll talk about some experimental evidence that goes with that as well. And the first thing to say there is that AToM, in this case, takes an explicitly developmental view, right? Whereas with theory versus simulation, we're taking kind of a hybrid approach and saying, well, they're both correct to an extent. Here, AToM is solidly on the developmental side. Right? We believe that theory of mind is developed as theory of mind, and it's not a process and not something that you're automatically born with and that you have from infancy. Of course, there is evidence against that developmental view. The biggest is that role of those other skills, right? Language being one of them, but also working memory capacity, other executive function skills. But here's the thing, for AToM, theory of mind is a special case of reasoning by analogy. So we would expect that improvements in other skills or in executive function would also improve theory of mind. Now, that's not going to be sufficient, right? Theory of mind does need those experiences to build up on so that we have a wide array of generalizations to pull and kind of memories to think through. But we would expect it to get better as other kind of maturation happens. We do take a stronger stance about language in particular. And with language in particular, we do say that language development causally leads to theory of mind development. Not that it's sufficient, but that it's kind of a necessary step or one of some steps that the subset of which leads to a theory of mind. So to be a little bit more concrete about that, in the innate view, language allows children to express theory of mind, or maybe to understand what's being asked of them in a theory of mind task. In the developmental view, or at least our developmental view, some aspects of language give children the ability to perform some aspects of theory of mind, and they do that causally. Okay, so both say that language is needed in order for us to see that children have theory of mind, but in the developmental, we argue that children need that language in order to have theory of mind at all, not just to demonstrate it. And there is a solid amount of evidence for that. A lot of that comes from de Villiers and her colleagues. And in particular, they've looked at certain grammatical structures and how those grammatical structures lead to improved theory of mind reasoning. One of those grammatical structures that is particularly helpful is called the sentential complement. It's sentences like, the boy said he kissed Big Bird, where you have this inner nested sentence that the truth of which kind of depends on this outside sentence. Another example of that might be, the girl believes the earth is flat. Right? The earth is flat is a statement on its own that happens to be false. Hopefully we can agree on that. But the fact that she believes it overall is true. So you can have this sort of mismatch thanks to the sentential complement construction. There have been some empirical experiments that show how that works out. And Hale Tager-Flusberg ran one of those, and it's one that we have modeled with the analogical theory of mind. What they did is they ran a training study with 4-year-olds who failed theory of mind pretests and sentential complement pretests, which means that they didn't understand how the sentential complement worked prior to starting the experiment, and they also didn't have theory of mind, or at least couldn't pass the theory of mind test before starting the experiment. They then had those children split into 3 different training conditions. The sentential complement, where they learned that form that we were just talking about, where the boy said that he kissed Big Bird, but really he kissed Grover, right? Examples like that. Another set of children learned the relative clause construction, which is another complex grammatical form, sentences like, Bert hugged the girl that jumped up and down. And so again, there's that kind of, there's the girl that jumped up and down, but you don't have that complete inner sentence, if that makes sense. And then some were trained on explicitly on false belief. False belief is kind of a standard set of tests for how theory of mind is tested in children. And that example that we saw earlier with the girl with the crayon box that has rocks in it is one of those example tests. And what the experimenters saw was that children improved on those theory of mind post-tests in the sentential complement condition and in the false belief condition. So when they learned that sentential complement construction and when they were trained directly on the tests that they would be tested on. But they did not improve when they learned that relative clause. right? So it's not just the fact that they learned something new that helps them, but there's something specific about this intentional clause that's helpful. And the AToM model gives us an idea of why that might be. So for the purposes of the model, just like with the children, we trained it using the intentional complement. Then we wiped the slate clean, trained it using the relative clause, and in both cases saw how it would then perform on false belief. Really important to this training are going to be the representations. And it turns out, and maybe we can talk about this more in the Q&A, but it turns out the representations play a really big role in all of this. But we'll get to that. So for the sentential complement, we notice that there is a nested phrase, right? The boy said that he kissed Big Bird, right? There's that nested phrase. And there's an explicitly marked contradiction, but really. There's a difference between what he said happened and what actually happened. So the representation looks kind of like this, right? This is going to be an image view of the representation. But we have this nested, he kissed Big Bird. And outside the nesting, the actual he kissed Grover. And we're going to mark that contradiction between those two things. On the other hand, when we're talking about the relative clause training, right, that Bert hugged the girl that jumped up and down example, there is no nested structure. So we just kind of end up with the clause all on its own here, the verb phrase. When representing the false belief scenario, there is some nesting here as well. And in particular, the nesting is of the belief that the person has because it's different from what the reality is. Right, so here we have that nested crayon, that she believes that crayon boxes hold crayons. And then in kind of the real world and what is being observed, the box holds rocks. But there is no contradiction because really we're just kind of looking at a picture of what's going on. So when trying to test on this, when trying to ask children what they would expect to happen here, there's going to be an alignment between the sentential complement representation on the left and the false belief representation on the right, using that structure mapping as we talked about before. And based on that alignment, we're going to be able to infer the contradiction. And so we would expect the child to learn that there can be a contradiction between what somebody believes and what is true in reality. And so they would be able to perform false belief reasoning or perform well on these false belief tasks, which is what Hale and Tager-Flusberg saw. On the other hand, for the relative clause, what we see when we try to align the relative clause construction with the false belief representation is that, well, nothing really. There's not really a great analogy to have here, and not really any good inferences. So and certainly no inferences that would allow us to perform false belief reasoning, or that would allow a child to perform false belief reasoning. And we believe that this is why, where that distinction comes in, right? Why when learning sentential complement, children did become better at theory of mind or false belief reasoning, and why they didn't when they learned the relative clause. So just to sum up, the model after sentential complement training passed the false belief test, just like the children did. And this is due to the nesting and the contradiction in that representation in the grammatical form, and but mostly the fact that it got the appropriate inference from analogy based on that representation. On the other hand, after the relative clause training, it couldn't pass the false belief test. And that's because it couldn't get candidate inferences from analogy that would allow it to do that. So again, we would expect children to have the same difficulty. So overall, from our big takeaways from language first, learning the potential complement grammatical structure improves children's theory of mind reasoning. I cited a couple of papers that showed that, and we went in depth into one, but there's actually quite a bit of evidence that shows specifically the potential complement. And then the other big takeaway from this is that AToM does provide a process level account for how language improves theory of mind. It is the same as the other theory of mind learning processes, kind of that same first general example that I gave at the beginning of the talk. And it also explains why it's specifically syntactical complement and why the relative clause doesn't really work in the same way. So now we've kind of talked about children. We've talked about the fact that they make mistakes in theory of mind reasoning, especially when they're very young. But we also said that by about age 5, they're pretty close to perfect, or at least pretty close to what their reasoning will be as adults. And most of the literature does focus on children, just because they seem to top out at age 5, and beyond that, it's a lot less interesting. But the fact of it is that adults do make mistakes. And that poses some really interesting questions, especially for developmental and theory models of theory of mind. Because if you have learned theory of mind, you shouldn't have problems with it anymore. But it turns out that we do. So most of those mistakes happen when adults make quick judgments. And most of those mistakes do seem to be because of that egocentric bias that we talked about before. And we talked about the fact that AToM gives an explanation for why we might have that egocentric bias, and that it's because of the memory retrieval. But it actually turns out that the story isn't quite that simple. And there's a lot more to those mistakes, especially as adults make them in everyday reasoning. There's a lot of evidence that those mistakes are actually very common in our everyday reasoning. It's just that we tend to catch ourselves. So we make an initial judgment that's incorrect, and then we fairly quickly correct ourselves and act usually on the corrected judgment. And because of that evidence, Apperly and Butterfield have proposed that there are actually 2 systems for theory of mind, similar to Kahneman and Tversky's thinking fast and slow for reasoning more broadly, but this is specifically for theory of mind. And they propose that we have one system that's efficient but inflexible, doesn't necessarily take mental states into account, at least not explicitly, and then a second one that's slower, that does encode all those mental states, but that requires substantial cognitive effort. Of course, most models of process theory of mind reasoning don't really have a ready explanation for how this works. Usually a model is going to give you an answer, whether that answer is correct or incorrect. And whether it has a way to correct itself tends to be kind of a separate question. And at least as far as I know, models of theory of mind reasoning haven't really addressed this. And AToM, at least the version that we've discussed so far, doesn't address it either. But it turns out that a relatively small extension to AToM can explain this phenomenon, and it explains it in what at least I think is kind of an interesting way. So for AToM, efficient and effortful theory of mind is actually just a single process of analogical retrieval and re-representation and re-retrieval and re-representation, etc. And so it's the same exact AToM that we've been working with, it's just that it can do it multiple times as needed. So let's kind of consider this example, and we'll use the basic kind of AToM that we've been talking about so far in reasoning through it. At this stage, we aren't talking about development anymore, right? We're talking about adults. So we're assuming that the person has all of the reasoning that they need, they have the memories that they need, right? And we're just observing the situation and trying to think through what the other person might believe. So suppose you see a new colleague and they're walking to the kitchen, and then you happen to know that they have the goal of getting some coffee. You've, of course, seen your colleagues go to the kitchen before, Right, that's this on the right. You've probably also seen colleagues have the goal of having coffee in the kitchen before. And in this example, maybe that colleague was surprised. Right? Maybe there weren't any mugs in the kitchen for them to use, for example. Both of these memories share some structure with the ongoing scenario of watching our colleague walk to the kitchen, wanting to get some coffee from there. But the one on the left has more of that structural alignment, more of that structural overlap. And so from this, we might be able to predict that the person we're currently observing is also going to be surprised to not find that there are any mugs. Now, you'll notice that this requires fully representing everything we know, everything that we can observe about the colleague at once, including their mental state, the fact that they want to get coffee from the kitchen. And the reality is that we are unlikely to know that. And even if we did, we're unlikely to have these really complete representations of the ongoing scenario in order to make those rapid judgments. And so we argue that that is going to be a big cause of those initial mistakes in theory of mind reasoning. To model the more extended version, we allow for re-representation and retrieval. So initially, we observe, initially, we observe our new colleague walking to the kitchen. We retrieve some memory that colleagues often go to the kitchen to get coffee. Maybe that's what they want to do too. That's going to be our initial efficient retrieval. Colleague wants to get coffee. And maybe that's sufficient. You know, I see my colleague going to the kitchen. I think they might want to get coffee. I might wave at them. Great. That might be the end of our interaction. But I might notice an anomaly, right? I might notice that when I've seen colleagues go to the kitchen in the past, they've always carried a mug with them. And this colleague doesn't have one. So with that anomaly, we might actually re-represent the current situation, the situation that we're observing, to include and maybe even highlight the fact that there isn't a mug in our colleague's hand. And based on that, we would re-retrieve. From that, we would retrieve that example case of a colleague who went to the kitchen and was surprised not to find any mugs there. And we might infer that the current colleague is going to be surprised. And at this point, again, one of several things could happen depending on how much cognitive effort we're actually willing to exert on this situation. Right? Maybe I'm done. Maybe I don't really care anymore. And in that case, maybe I'll intervene and shout out that, hey, there aren't any cups over there. Maybe I'll let it go. But I've kind of made all the inferences that I intend to make. Alternatively, I might decide that I'm willing to expand a little bit more effort. And in that case, I might re-represent again. Maybe I'll remember that the colleague told me earlier that they don't like coffee, right? And I'll have to re-represent that part of the situation, re-retrieve again, and maybe now I'll realize that, oh, they're actually just going to the kitchen or to look out the window. There's a nice view out there, something like that. Right? So this allows AToM to make theory of mind judgments kind of based on the amount of effort that we're willing to put into a situation, which matches up to that efficient versus effortful distinction that Apperly and Butterfield make, but without having to have two separate processes, right? It's still all the same process. It just depends how many times am I willing to re-represent and re-retrieve, re-represent and re-retrieve. So the takeaway from this model then is that adults' mistakes and corrections in theory of mind reasoning do pose a problem for many theory of mind theories, but a small extension AToM seems to overcome these mistakes. And although we haven't really tested yet whether this extended version of AToM works exactly the same way on the previously discussed experiments, we expect that it will, because the process actually hasn't changed. Right? It is still the same: represent, analogically retrieve, and reason through candidate inferences. It's just a matter of, am I satisfied with that initial judgment, or do I spot something that makes me want to go back and try again? So general takeaways from the two modeling experiments that we've talked about. Theory of mind reasoning is necessary for social reasoning. Hopefully you remember that from my very first slide. And there are many unsettled debates about the processes of theory of mind. But analogical theory of mind seems to provide some answers to these debates. Right, so, and it does that because, first of all, it's a theory and simulation hybrid, which lets it take the best of both worlds from both. It's developmental, and it explains some of those developmental findings and how they play into the bigger picture. And it can be both efficient and effortful using the same processes of analogy, making it kind of tying a nice bow on it, so to say, in some ways. So does that mean that AToM settles all of these debates? Of course not. There are many more that we just don't have time to talk about today, and frankly, ones that I haven't had time to look into and experiment with. Among them is how second order theory of mind would work given an AToM type model. The second order theory of mind is what I think you might think about somebody else. So it's a step removed. And it is a little bit more complicated. There's some really interesting evidence that we find it hard to do and that it's an effortful process for us every time. And that's actually something that I'm working on with a really brilliant undergrad here at Oxy, who's been working on trying to model what second order theory of mind might look like. She will likely be applying to grad school next fall, so keep an eye out. But that is a big question overall. The second order theory of mind does complicate things. There's also the question of whether that efficient and effortful version of the AToM model works with the empirical studies. The proof of concept example I gave you is more or less as far as we've gotten with that model at this point. But there are, of course, a lot of empirical experiments that show the kinds of mistakes that people make and when they correct for them, and to some extent, the amount of effort that they need to expand in order to correct those mistakes. So that's sort of on the docket, is testing with those experiments. And finally, looking into how AToM's predictions play out in the real world. I didn't really speak about the predictions that AToM makes today, but it does make some really interesting ones. And if any of my psychologist colleagues are interested in collaborating on some empirical tests for those predictions, I would be really interested to work with you to look into some of them. Of course, that is still not the complete list of things that we need to look into, but it is a start, and hopefully I've convinced you at least a little bit that analogy might be a good explanation for theory of mind reasoning. Thank you very much. I'm very happy to take questions now. My email is also up if you think of something later. I'm happy to answer questions at any point.